This is hypothesis tests. And we have two parts to a hypothesis test. One is the null hypothesis. It's called the null hypothesis because they write it with a 0, the h sub 0. The other is the alternative. And the alternative is what people want to demonstrate is correct. It's not necessarily right. It's just more correct than the null hypothesis. If this were a medical experiment, the null hypothesis would be that the medicine doesn't work. The alternate would be that the medicine does work. And this is because in statistics you can never say anything is right. All you can do is reject the null hypothesis or fail to reject the null hypothesis in favor of the alternative. So we can never say we accept the alternative. You never get to accept anything. You can reject or fail to reject, and all of it is on the null hypothesis. If I reject the null hypothesis, then I'm going to act like the alternative is true. And this is also written with an A at the bottom as a subscript, HA. So some people do it one way, some people do it the other, and it doesn't matter which way it is. In these, you get three kinds of null hypothesis. And this is a two-sided hypothesis. The mean is equal to some hypothesized value, 6. The mean is equal to 6. The mean is equal to 30, whatever. And the alternative is everything that the null hypothesis isn't. That's different. You write in one place and it shows up in a slightly different spot. So it's either equal to this or it's not. We got ball bearings, they're within this range or they're not. This is two-sided because it's where my answer would land if I'm going to reject the null hypothesis. You do an experiment, you get a t or a z value from the experiment. And where that value lands determines what you do, what your conclusion is. And this is where the alpha comes back in. Say alpha is equal to 0.05. If it's a two-tailed hypothesis, I want 2.5% in each tail. So that if my t value, and this is just pure t, here's a 0, this is about 2, about minus 2. They're not exact. If my answer lies in any one or either side of these, then I can reject the null hypothesis. These are called the rejection regions or the critical regions. If my answer doesn't land in one of those tails, then I fail to reject the null hypothesis. So two-sided, the alpha level, the chance of error, is split between the two ends. And in this case, I would have a t value And the t-value is the same on both ends except for the sign, and the probability is alpha over 2 with n minus 1 degrees of freedom. And this is just the way they write it for convenience. I've got a cutoff value. This is called the critical value because it cuts off the critical region where my answer falls and I reject the null hypothesis. So that if I had an experiment with n equals 30, and I want alpha equals 0.05 for my error, I need to look up a t-value that cuts off 2.5%, 0.025, with 29 degrees of freedom. All right, this is where you need XL. And this is the usual t command, equals t dot inv. The probability that we're going to look up is either 0.025 or 0.975, the other end. So if you put in 0.025, because that's the easiest, and we have to have degrees of freedom, n minus 1, this says the t-value, the critical value that defines the rejection region, is 2.04. So if I do the experiment and I get an answer, I'm going to get a t statistic out of this hypothesis, out of this experiment, and the t-value is either bigger than 2.04 or less than 2.04, then I'm going to reject the null hypothesis. If it's anywhere in the middle, and I don't care where it is in the middle, I fail to reject. So the critical region is the big deal. It's defined in size by the alpha level, the chance of a mistake. I want a 1 in 20 chance of a mistake. Alpha equals 0.05. Two-tailed test, it's split on both ends. This is just exactly like a confidence interval. A one-tailed test, I can have two directions. This has a null hypothesis that the real mean is bigger than some amount. And this would be like, I'm giving blood pressure medicine to people. If the medicine works, the blood pressure goes down. If it doesn't work, then the blood pressure doesn't go down. So that this is one-sided, same alpha level, but the alternative always points to the rejection region, to the critical region. The alternative points down. So all of my 0.05 is in one tail. One-tailed test, if the answer falls past that point, I reject the null hypothesis. If it doesn't, I fail to reject the null hypothesis. So this is the critical region, or the rejection region. For this one, I need, say we have the same sample size, the same alpha level, except now all 5% is in that one tail. So for the XL command, I have t.inv and all 0.05 is in the tail, and it's on the lower end. And I have 29 degrees of freedom. And I need to put in an equal sign. Equals. There we go. So this one is minus 1.7. So I do my experiment, and if my result comes out with a t-value less than 1.7, I reject the null hypothesis. This is the rejection region, the critical region. If it comes out over here anywhere, I don't care. I failed to reject. This is traditional statistics. I got a 5% chance of error. If it falls in there, I reject it. If it doesn't, I don't reject it. All right, the deal is, what if I got a t-value from my experiment of minus 9? Where is minus 9 on this scale? Way down there. That's the technical term. It isn't possible that the null hypothesis is true. I got a minus 9. Traditional statistics, it's past minus 0.7. I don't care where it is. The other way this can go is the other direction, where the mean is less than something. This is like the corn yield, the fertilizer experiment. I put out fertilizer, and if it doesn't work, the corn yield doesn't go up. It's this level or lower. The alternative is that the fertilizer works. And here, everything is in the upper end. The result falls in this area, I reject the null hypothesis. If it doesn't, I fail to reject. So this is the whole key. The alternative points to the rejection region. For example, if I got here, I hypothesize that the fertilizer is 100 bushels to the acre. Mu is less than or equal to 100. If I get an answer back here, say it comes up 90. I'm back in here, and there is no chance that I could be up here. If this is my rejection region and I get less than my hypothesized value, there's no need to even check. It's out. So remember what these things are trying to do. If it's two-tailed, not equal, in the alternative, I have both ends and I have to split the alpha level. If it's on one end, low end, I put all of it on that end. If it's on the other end, I put all 0.05 on the upper end. Those are the rejection regions. That's where my answer has to land to decide what to do with the experiment. For this one, with 0.05, this is the 0.95. N equals 30. Alpha equals 0.05. What is the cutoff value here? What is the t value that cuts off 95% to the left, 5% to the right? Look at the one above it. this cutoff 95% to the right, 5% to the left, and the t-value was minus 1.7. The only thing that changed is which end I'm working on. Right, so we do the experiment, we get a t-value. This is called the test statistic. And we'll get to calculate that. We get a t-value from our experiment and we compare it to our hypothesis layout. Okay. On this, we've got hypotheses and we've got T and P, or Z. Look at the first one. I have an experiment with sample size of 57. The null hypothesis is that the mean is equal to 18. The alternative is that it is not 18. I don't care whether it's bigger or smaller, it's just not 18. The alpha level is 0.01. I need to find where the cutoff limits are. My chance of a mistake here is 0.01, 1 out of 100. This is pretty firm result if I get it. Use the sheet, and it's got a Z or a T scale on it. Put on there where the rejection region is. And we're going to find the cutoff values for that. Here's a line, 0, 1, 2, 3. Where is the rejection region? Where does the alternative point? It's not equal. It points both ways. So that I have a critical region, a rejection region, up on this end and on this end. Total is 0.01. How much in each end? 0.005. Just divide it by 2. So I've got 0.005 here and 0.005 here. I need the t-value that cuts off the critical region. And it's going to be plus and minus. It's the same thing because I got the same amount of area on both ends. What's the command in Excel to get that t-value? t.inv. t.inv. What probability am I going to give it? 0.005. And how many degrees of freedom? 56. Sample size is 57. 56. Darn. Equals. The cutoff value is minus 2.66. 2.67. This side is plus 2.67. If my answer, my result falls in this end or in this end, I'm going to reject the null hypothesis. Otherwise, I fail to reject. Those are the critical regions, and that's all I have to do to find them. So for this one, 2.67 up, minus 2.67 down, and I got my setup. If I wanted to look up this t value, what would I have to do? In Excel, how do I get the other end? This one I gave it 0.005. What's the other end? How much have I got in the middle? If I got 0.01 outside on both ends, what's in the middle? 0.99. I need to look up 0.995. I add my 0.99 to the 0.005 to get the upper end. So it's equals t.inv 0.995, 57 degrees of freedom. Pardon?
Is it 56?
56 degrees of freedom. Yes, it is. Sample size is 57. And there's the positive version. When we had to look this up in a table, basically we only needed 1/2 of the table. We always used the bottom half of the table. Because if you wanted 0.995, you looked up 0.005 and made it positive. Same thing here. This is just which one we want to look at. What's convenient. And the good thing is that if you're looking on both ends, one of them's got to be negative, the other's got to be positive. It's hard to confuse. Look at number 2. What's the difference between number 2 and number 1? Sample size is different. The null hypothesis is that the p-value, some population proportion, is greater than half. The alternative is that it's not greater than half, it is less than half. I'm checking coin flips. Does heads come up more times than it should? Is the coin fair? Where's the rejection region and how big is it? The chance of error, the area of the rejection region is 0.1, 10%. Where is the critical region? Here's 0. Where does the alternative point? The lower end. And also, if I got a result of 0.6, I'm good. I'm past the null hypothesis. The only way I can reject it is if I'm less than half. So there's a lot of ways to remember this. What's my cutoff value for the rejection region? What's the alpha level? 0.1. It's on the low end. Now I have a proportion, and this is irritating at best. It's a proportion. I use a z value. I don't use t.inv. I use norm.s.inv. .s.inv. Think of this as z.inv instead of t.inv. What's the alpha level? What's the probability in that tail? 0.1. 10%. I'm going to put in 0.1. Look at the XL command. Equals norm .s.inv. This is the standard normal function, and all it wants is probability. There's no degrees of freedom for this. Put in 0.1. The critical value is minus 1.28. So if my experiment gives me an answer less than 1.28 negative, I'm going to reject the null hypothesis. This is the rejection region, the critical region. And it's called both things. What if the alternative and the null were the other direction? It'd be positive 1.3, and I'd have to look up 0.9 instead of 0.1, or I look up 0.1 and change the sign.